Well, welcome to this lecture. This lecture is on structure or geology. It is a lecture we're going to have on how to understand a mountain range or a mountain. And it's in a general kind of knowledge. It's not a knowledge that's precise. This knowledge is not always true, but it's important to understand these concepts so that you can look at a mountain and make some judgment as to where water might be and whether it might be in the form of a spring or a tinaja. That tinaja is a Spanish word for tub or bowl, which is often used in some parts of the desert to mean this depression that's watertight, and when it rains it fills with water and holds it for a period of time, and basically animals use it. In other parts of the desert, this same phenomenon is called a water pocket. And it's the same thing. An erosion will cause a pocket or a depression in the rock and holds water, and the wildlife use it. So let's get started with our lecture here. We're going to start with a fairly normal mountain, as we've talked about before. And this mountain is primarily made of stone. And of course we have all the runoff issues and so forth. And one of the first things we can discuss is if it rains, if we look at this top little piece of the mountain up here, make a contour line right up there, we only maybe have, let's say, an acre up there. Well, that means we only have an acre of water being collected that's available for runoff. Now, many times this particular part of the mountain is pure stone, and it runs off virtually everything that hits it with rain. And then if we go down to here and we make a contour line at this point, we might have several hundred acres, many times the size as it goes down. And that's a way of collecting water. That surface area is going to collect water, and it's going to start to channel it. And by channeling it, it's focusing the water. And as it focuses that water, the different lines of strata now in the mountain, regardless of how they could be, like a granite, is often very erratic. It'll have all kinds of cracks and fissures, and even quartz layers that are layered in odd directions. But as the amount of water increases, these imperfections in the mountain become more and more important, because each imperfection can either stop water or channel it into the interior of the mountain. And if we have, say, a very hard layer up here that's very resistant to erosion, it might hold the mountain out this way and then starts again in a softer layer of strata that continues. And so we see this bulge on the mountain. Well, that bulge can do any number of things. It might be as the water's coming down, and now it's got a crack and it comes back, the water comes back and down into the internal part of the mountain. Or it might spill over the top and right here dig out an erosion area, and there's our water pocket, or tinaja, the bowl that's going to hold water. But this tinaja can't happen way up here because it just doesn't have the velocity, and it hasn't had that step off of that harder material to drop and dig out the tinaja. So as we go further and further down the mountain, more and more this happens, depending on the size of the mountain. Of course, you can have a mountain anywhere from a couple of hundred feet to thousands of feet, tens of thousands, 10,000 foot tall mountain, having all these different things working on it. And as it works on it, and as you go further down, you have this scenario is more likely. And if it happens down here, let's say, it repeats itself. We have another hard layer of stone in the mountain, and the same drop off to another soft piece of rock. Well, this one is far more likely to collect water and channel it into the internal parts of the mountain than it is up here, simply because this one's going to have more surface area collecting more water. So you almost never find a spring high up. That's because it hasn't collected the water and hasn't had as many chances, if you will, to get the right strata layer right, where it's soft or permeable or impermeable. You haven't had the odds get better as you go down. It's kind of a numbers game. And when you get up to a mountain and you're looking at it and you're saying, well, where should I look? You know, where can I find this kind of an action? Start looking at the various strata layers, look at the plant life. A lot of times, if you look at a mountain, say it's a range, and you say, you know, there's an increase right at this level of plant life. You look down the other end of the range, you might see those same layerings. Well, that's a clue where to look for water, whether it's a spring or it's an aha. It depends on what you're looking for. Now, once you get down here, you have another situation that begins to occur, because you have more debris. In the cases of a mountain like 1,000 to 2,000, 5,000 foot tall mountain, this channel, if we have a channel cutting down through here, the canyon, gets to where it can actually move house-sized boulders. And when you're moving house-sized boulders, it's pounding and grinding its way down the canyon. It's taking out a lot of material, and it's taking it out relatively fast. And so you can move a boulder down here, whereas up here you're lucky if you get a few grains of sand moving. So as you go down the canyon, most of the time or often, you get an increased rate of erosion. And so you end up, we could probably draw this with a little better situation. This mountain's pretty steep to kind of show that in drawing, but it would happen either way. Let's say we have a mountain like this. Now, the erosion is happening from, of course, the top to the bottom. But if we were looking sideways through the mountain, you can visualize that. This canyon would get deeper, steeper, 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 like that. If you were looking, this is the edge, this is the top of the canyon, and as the erosion increases in the boulders, it starts cutting deeper and deeper into that bedrock of that mountain. And what it does when it does that, again, it's kind of a numbers game. As it cuts in, there's an increased likelihood that it's going to find the aquifer that's been starting up here at some layer up here. The runoff has, say, finally gotten back into the mountain here, and it's come along this mountain, this layer, and then it's found a crack, and now it's pouring down through here, and now it comes out here somewhere as a spring. Oftentimes, you'll find this spring in one of two manners. It'll either be right down the very center of the gorge, and it'll be, if it's a big enough mountain and a proper enough aquifer, you'll have a little creek that might only be 30 or 40 yards long, but it's right down the center. It's right down the center, and that's no accident. It's because that water has cut right down into that thing. Another thing you'll find that sometimes as you're walking up one of these deep canyons, and as you get close to the point where you're going from the alluvial to the bedrock, look off to the right or left, and a lot of times you'll find a crack or a layer of rock that actually has a spring. And oftentimes these springs are not just a single point spring, but rather might be 10 or 20 yards long and paralleling some of the geology, paralleling whether it's it might be at an angle, oftentimes following a quartz vein, or it might be in a sedimentary rock. It'll be just right in one of the layers of sediment that's the right rock that has the right place, that got cut the right place. and now water's coming right out of that particular layer. And a lot of times you'll find it even, that layer hit and miss all the way around you as springs. But it's because the erosion is cut deep down into that. You don't normally find springs way down on an alluvial, although it can happen. That's where you get into this idea that it's an art and not a science. Working these kind of things, you can kind of play a numbers game, but it's still an art. It's not really a hard science. And the same way with the Tanahas. You're going to find as it drops, as this erosion gets greater and greater, the force of the water is carrying better and better boulders, and even the sand and the grit that's following along with it has more velocity, and it has simply more sand and grit because it's been collected from all these other side canyons coming down. And so there's more force available to dig out a Tanaha on the lower end of the mountain as opposed to the upper end. So with more force available, more grinding material available, and more water available to move that increased grinding material, all you need to have is the right layering, and you will get these bigger, better Tanahas that are full of water and that wildlife will center on. And bigger is better when it comes to Tanahas, both bigger and deeper. In the sun, if the Tanaha's out in the sun, it will evaporate as much as an inch a day. And that's assuming that it's absolutely watertight. It will still lose an inch a day in the summer, just from evaporation. So a Tanaha or a water pocket that's 30 inches deep, you can look at it and say, you know, if watertight, it will last about 30 days. So if something is 6 foot deep, that's 2 months. Well, that's like having water July and August. And if it's big enough, say 5, 6 foot in diameter, where the first animal drinking out of it isn't going to drink it dry, a 6, 8 foot diameter Tanaha or water pocket that's 3 feet deep is a significant water source in the desert. It's just really a very significant water source, and a lot of animals, your coyotes, bighorn sheep, deer, etc., badger, you name it, is going to know of its presence. They'll know it from a herd memory. Sheep will know it from a herd memory. And other animals, like a coyote or something, will actually smell it oftentimes and can find it that way. So these water pockets and springs do follow a certain pattern, but it's not always there. And that's really the hard part of learning this, is to understand that it's not always there. But when it is there, it oftentimes follows these patterns of existence. And once you start to understand that, you have a better chance of finding water in the desert. And of course, that's a key resource. And with that, I thank you for listening to this lecture, and we'll see you.